This class is supposed to be an English class, and we are going to use English only. Okay? I think we're going to have one midterm and one final. But if you guys don't want to have a midterm, we can probably we don't have to have it. Just one final if you want. We have pretty many students here. Are you guys all graduate students? Who is from outside the material science department? Where are you guys from? Chemical engineering? Huh? Okay. Let's see. Have you guys seen the YouTube for the introduction of this course? How many of you have seen that? Our lecture is going to be uploaded to the YouTube so that even if you miss the class, you can, don't worry, you can have it through the YouTube, okay? So please don't come to the class every time. If you are busy, you don't have to come. I'm not going to call you up in the class. The attendance has no meaning at all. Okay, and everything on the text has been uploaded to the computer PDF file, right? You guys have seen that? The content of it has been uploaded as a PDF file.
Sent to all students.
You have sent them all? So before you come to the class, please read the content that is going to be discussed in the class in advance. And then if you know everything there, then you don't have to come here. Don't waste your time. All right? And you can get the lecture through the YouTube later. So. Okay, we don't have a regular textbook, but the text that I made has been uploaded as a PDF file, so you can look up to it anytime you want. All right? Okay, my name is Seung-ki, and 5563 is my extension. My office in the third floor of this building. So please call me before you visit my office if you have any business. Okay? All right, our class title is Defect Chemistry. Defect. When we talk about the defect, it's something less desirable, or should I say something negative, right? But our course is about defects. Why? The defect is the thing that controls the material properties. That's very interesting, right? The defect is something less desirable, but that is the thing that controls the material properties. Like, for example, the mechanical strength that is depend on the defect density, like a dislocation density is. You guys know how to make steel strong, right? Strengthening mechanism is one of the strengthening mechanism of the steel is to generate the defects, dislocations, number of defects. And most of the electrical properties is related to the point defects. Point defects. This point defects is very much different from like line defects and the volume defect, three-dimensional defect. The typical example of a line defect is the dislocations. Dislocation. And grain boundaries, things like that. Okay? The volume defect may be crack, void, things like that. We have actually two-dimensional defect as well. That is a surface. Surface is a kind of defect in a material, right? And the point defects is related to the electrical, optical, magnetic properties of the materials mostly. And this point defects is different from the line defects and volume defect and two-dimensional defect in a sense that this point defect has equilibrium values. Equilibrium values. That is a striking difference between among these defects. Okay. Equilibrium value. What does that mean? It means that the density or distribution, these kind of things are predictable. That is what this equilibrium value means. Okay, equilibrium value means we have the density, for example, is some values times e to the e star of kt, where e star is going to be called activation energy. Activation energy. That point defect can be described in these equations, and if it can be expressed in this equation, it means that it is predictable. The density and the distribution is predictable. Why? Because if you take a log of this, then that is going to be E star over K 1 over T. Things like this. So if you have plot the density and 1 over T, then we are going to have a straight line, beautiful straight line. This straight line means that we can predict the values at extreme ends. Okay? And this slope is going to be the activation energies, which controls the basic mechanisms, what that point defect can be generated and then transported, whatever. So predictable and reproducible. And importantly, that is the thermodynamic quantities. Okay, this thermodynamic quantity means actually that is the equilibrium values. So, for example, if you want to make a, you know that if you want to make a steel strong, you have to generate the large number of dislocations. But that is not, there is no equilibrium values for the dislocation density in a steel. In other words, the number of dislocations is not directly related to the strength of the materials. You just know if you have a many number of dislocations, then your material gets harder. But it's not, it doesn't have equilibrium values. However, the point defect has equilibrium values so that we can approach to the material properties related to the point defects like optical properties, electrical properties, theoretically. All right, what kind of defects do we have as a point defects? Well, the atomic defects, the vacancies, interstitials, you guys know, and the misplaced atoms, which is the substitutional defects, and the foreign atoms, of course, it's kind of a point defects. And also, we do have electronic defects, which is electrons and holes. Those are the defects. So in this defect chemistry, we are going to deal with not only the ions, but also the electrons and holes as well. So it is kind of electrochemistry, right? How come you guys are so serious? Hey, relax. It's just the introductory course, so you don't have to get stressed in any way. You guys have all good grades, by the way, because you are graduate students, right? Two major questions to be answered in this class about the point defects are, first, identity and concentration, which is related to the thermodynamics, okay? And secondly, the transport properties in response to external forces, and that is related to the kinetics. Okay, so we are going to approach the kinetics and thermodynamics of point defects in this class. Okay. Now the external forces here, we are concerning only the electrostatic potential and the chemical potential, so that the potentials that we are going to talk about here is the electrochemical potential, which is going to be written as eta, okay? And then that is the chemical potential and the electrostatic potential, chemical potential and electrostatic potential. We do have other potentials like gravitational potentials, whatever, but we just ignore that. We just think about the chemical potential and electrostatic potential only. And in a metallic system, we are going to talk about the metallic system in the first part of our lecture, just briefly. But in metallic system, we do not have electrostatic potential because there are so many electrons in the holes. So we do not have electrostatic potentials in the metallic system. We only have chemical potentials only. But in the non-metallic system, we do have electrostatic potential as well as the chemical potentials. So we always have to think about chemical potentials. So we mainly discuss about the electrochemistries. Electrochemistry. What is electrochemistry? That is the electrical control of the chemical reactions. We can say electrical control of chemical reactions. That's fantastic, isn't it? We can control the chemical reactions to make any new materials or whatever by electrically, and that is very nice. Okay, and a typical example of this system, and the system that we are going to discuss mainly in this class, is the batteries. Is the typical example of electrochemistries. And in the batteries, we have a cathode, and electrolyte, and anode. Okay. And the cathode, we usually say Ma, mixed conductors, and electrolyte, we have electroactive species as A plus A ion, and then anode is just a metallic system of A. That is a typical example of the batteries, and the electroactive species is A plus in this case, A ions. So we make external contact of this, and then we control the chemical reactions happening inside a battery through the electrolyte. Okay? And of course, the electrolyte, only the ions can move, and electrons and holes, there's no electrons and holes moving inside the electrolyte. And the electrons and holes are moving through the external circuit only. That is the battery system. Now, let's just take a look at the inside the batteries briefly, so that we can have an idea what kind of topics we are going to deal with in this class. Okay? Let me give you some ideas what's happening inside the battery system. And here, if you see, this is a cathode surface. And here is the electrolyte, and this is the anode surface. Okay, and then, for example, if you have a discharging reactions, for example, and then what's going to happen here at the anode is that the A atoms is going to be ionized into the A plus, and then electrons, which is coming out from here, A is going to render one electron, and that electron is going to go out through the external circuit. And then they're going to reach through this cathode surface, and we can measure the current, the number of electrons passing through that happened from these chemical reactions. And the cathode surface, what we are going to have is that this A plus ion electroactive species is going to meet the electrons and then form a neutral A, the atomic A here, okay? And then this A is going to chemical diffusion inside this cathode material. Now, the importance of this reaction is that the potential or the EMF, the voltage of this cell is going to be determined from activity of A electroactive species and electroactive species here. Then if you use a pure metal for anode, then this is going to be 1, okay? So that the voltage that we are going to have here is activity of a cathode. Now, if you are working on the dilute concentration of A here, or the high concentration of A, we can apply Henry's law or the Raoult's law so that we have activity coefficient, which is constant, which means that the concentration is going to be related with the activity coefficient like this, which is a constant value. Okay? So that is directly related to the concentration of electroactive species A in the surface, at the surface, I should say, of the cathode material here. Now, what's going to happen at the very beginning of this discharging reactions? Then, as you can see, this is the surface, and that is the length L of the cathode material, and the concentration of electrospecies A is going to, the profile is going to look like this at the very beginning of this discharging reactions, right? Now, this one is going to diffuse into this cathode material through the diffusion coefficient. And this incoming flux of electroactive species A is from the values that we apply through the voltage or the current. We control the flux of A reaching to the surface of this material. But this concentration of electroactive species A will diffuse into the cathode material through the fixed second law or fixed first law, right? What does the fixed first law says? The flux that is moving is related to the concentration gradient in a manner like straight line, and that is the diffusion coefficient. That's what the fixed first law is about, okay? So if we artificially push some of the flux of electroactive species electrically through the external circuit and then put some amount of A to the surface of A material, then this A material electroactive species has a concentration profile like this, and it's going to move it towards the inside the cathode material by the Fick's first law. Okay. Now, the voltage of the cell is determined by the concentration of electroactive species at the surface. Okay. If you want to maintain the high voltages, for example, then this A should be diffused into the material as fast as it can. Okay, then you can maintain the high voltages. But if the electroactive species is accumulated at the surface, so that the high concentration is maintained at the surface, then we cannot have high voltage, high capacity of the material. Which means if you want a high capacity materials, cathode, batteries, then your material, your cathode should have a high diffusion coefficient of the electroactive species A inside the material. So naturally, what we are going to discuss in this class is that equilibrium concentration of A at the cathode surface. Okay, that is defect equilibrium. Defect equilibrium. That is the main concern of our discussions. There should be. Okay, and then secondly, we have to deal with the diffusion of A inside the cathode material, the kinetics. So the first part, the equilibrium concentration, is related to the thermodynamic quantities of the materials, cathode material. And the second thing is the kinetics. Okay, the transport, mass transport are the defects. So first half of this lecture consists of thermodynamics of defect concentration, defect equilibrium, things like that. And the latter half is related to the mass transport kinetics, diffusion coefficient, fast ionic conduction mechanisms, and the active passive electrochemical devices like sensors, batteries, fuel cells, and things like that, etc., etc., etc. Okay? Are you guys happy? Any questions? I think that's about it for the first class. And then from the Wednesday, the day after tomorrow, we begin to talk about the defect equilibria in a metallic system first. That's rather simple. And then we get some idea what the defect equilibrium is about, and then we're going to approach the non-metallic system defect equilibria, which is directly related to the battery properties of the materials. Okay. Any questions? No questions. Okay. Oh, sure.
I want you to explain one more time how the accumulation of atomate on the cathode surface affects the voltage.
Why? You mean why it is accumulated?
How is accumulation affects the voltage?
Oh, that is related. You're questioning about this equation, right? Why the EMF voltage is related to the concentrations like this. that this equation is going to be called Nernst equation. And then that is a very important topic of our discussions in the class. So we're going to talk about this shortly. That's a very good question. All right, I'll see you on Wednesday then.